Okay, so today we're going to talk about double replacement reactions or precipitation reactions. These happen when we have two compounds coming together to form two new compounds, and they're usually happening in aqueous solutions. So in this reaction, what's happening is we have cations and anions essentially trading partners to form two new compounds. So we're getting two new compounds. All right. And we can say that these reactions are generally not going to take place. In other words, we can get a no reaction for this. If it does not form an insoluble ionic compound or a covalent compound. So in other words, if we put together, if both of these reactants are aqueous ionic solutions, and I put them together and I get two aqueous ionic solutions as products, that's not a reaction, okay? So if an insoluble solid does form, though, we are going to refer to that insoluble solid as a precipitate. Right? We've seen this before. So, for example, if I have lead 2 nitrate, PbNO32, and Ki, and they're both aqueous. So let's kind of talk about what that would look like on the particle level. We're going to draw like particle diagrams. So let's say for Pb, and this is Pb2+, I'm going to use this little red, we need to turn that into a little box. Somewhere in the box. So Pb is that guy, and then maybe we use black for nitrate. Nitrate is going to be a nitrogen surrounded by 3 oxygens. So there's a little nitrate molecule. Now these guys are separate in the solution, right? So you've got the Pb, and you've got a couple of nitrates floating around in the solution, and they are separate because they're aqueous, right? But I'm going to draw 2 nitrates for every 1 lead. Okay, in my aqueous solution. So we'll go back to red for Pb. Oops, sorry, let's keep red. Red for, one more time. Red for Pb2+. Okay, so that's what we mean by aqueous. They're separate. Now, if I switch over to, I don't know, we'll go with orange for K, and we'll go with green for I. And these guys are also aqueous, so that means for I've got an iodide, and I've also got an orange potassium. And again, they're separate from each other. They're floating around the solution, separated by water molecules. When they come together, at least 2 of these ions actually have to, form something new. So in this case, we've got PbI2 as our product that is a solid precipitate. And so what that means is in this test tube, the Pb, which was red over here, and the I, which was green over here, have come together to form little crystals of solid PbI2 in the bottom of the test tube. It's formed a precipitate. In other words, they've come together to form a clump of Pb's and I's in a 3-dimensional crystal like this. Okay. Now, the potassium nitrate may still be aqueous. So the potassium is up here surrounded by water molecules, and the nitrate is also up here surrounded by water molecules. They haven't really changed, right? So they're just kind of like spectators. They were aqueous to start with, and they're aqueous now. But the reason that we know we have a reaction is because the lead-2 and the iodides came together to form a solid precipitate that wasn't there before. So if we go ahead and talk about, okay, so how could we have possibly known without doing the reaction firsthand, how could we have predicted that this would have happened? In other words, how did we know that the PbI2 was going to come together and clump up and be insoluble like this and form a precipitate? Well, that's where our solubility chart comes in. And so you don't have to memorize this. You'll always be given this, but it's a chart of solubility rules for ions. And so if you look at this, we could have used this to predict that that the potassium nitrate would be aqueous and would just remain dissolved like it did up here. If I look at the rule for nitrates, which is the very first rule, so it says that NO3 minus ions. So in other words, when these guys are paired up with a positive ion, they will always be soluble and aqueous, and there are no exceptions. And so by that logic, anything that I put with nitrate, whether it's lead-2, copper-1, magnesium, aluminum, doesn't matter what I put with it, it will be soluble. So if any of my products end in NO3, no matter what the positive ion is, it is going to be written as aqueous, okay? And so that by itself does not show that a reaction has happened yet. We need a solid precipitate to form. So if we look at our PbI2, well, we can look at the rule for iodide because it is PbI2. It's got I- ions in it. And we can see that along with the other halogens that have -1 charges, iodide is typically soluble, but there are 3 exceptions, and lead 2+ is one of those exceptions. And so what that tells me is normally iodides, along with chlorides, fluorides, and bromides, tend to dissolve well in water. But when the positive ion is one of these 3, they tend to stick together and form precipitates. And so since PbI2, the lead-2, is one of those exceptions, that's why we had a solid precipitate form. Okay, so our PbI2 was solid, our KNO3 is aqueous, and so the fact that we got 1 solid out of this thing is what tells us that we have a reaction. Okay, let's try a couple of examples. Let's start with, okay, so let's say we start with some aqueous sodium carbonate, and we're going to try to react it with aqueous calcium hydroxide. Okay, so the first step is to figure out what are our potential products that we could get from this. And by that I mean, what is sodium now going to be paired with if it trades places with calcium, right? And so hopefully you said sodium hydroxide, right? So we have NaOH, it's a little sloppy, but you get the idea. And it is 1:1 plus 1 minus 1, right? And then what's our other product going to be? All right, well, it looks like calcium carbonate. So Ca, CO3, and then we check the charges, and calcium is 2+ and carbonate is 2-. So that one is also good. Now, before we worry about balancing it, we need one of these 2 to be an insoluble solid precipitate. And so I go through my rules, and I see that the rule for hydroxides says what? It says that hydroxides tend to be insoluble, but there are a bunch of exceptions, and sodium is one of those exceptions, right? So therefore, this sodium hydroxide, even though most hydroxides are insoluble, sodium hydroxide is soluble. It's an exception, right? We also have the rule down, this very last rule pertains to a couple of positive ions. Anytime basically sodium is your positive ion, it's going to be a soluble solution. So both of those rules tell me that this thing is going to be soluble and therefore aqueous. So we don't necessarily have a reaction yet, okay? So let's see what the other compound looks like. All right, so we've got carbonates. The rule for carbonates says that they are usually insoluble, right? So this is promising. This means it might just be a reaction. So, and there are 4 exceptions, but calcium is not one of those exceptions. So therefore, we would say calcium carbonate is insoluble, which means I'm going to put an S for solid next to it. So it's a little confusing. You might think S for soluble, but no, S means solid, which means insoluble, right? So therefore, this is a reaction, right? All right, and then the last step, of course, is to balance. So if I have 1 carbonate on the right and it looks like 1 on the left, that's good. 2 sodiums on the left, only 1 on the right, so we probably need a coefficient of 2 there. And that's going to give us 2 hydroxides, which is good because we have 2 hydroxides on the other side. And then it looks like 1 calcium and 1 calcium. So we're all set. This is a reaction. Okay. All right. Let's try another one. Let's try Okay, let's try lithium nitrate and barium sulfide. All right. Okay, so let's think about what's going to trade places here. Lithium is going to trade places with barium, and so our potential products would be lithium is now going to be paired with sulfide. And if I check the charges, lithium is +1, sulfide is -2, so that would be Li2S. And then my other potential product would be barium nitrate. And barium is +2 and nitrate is -1, so we will need 2 nitrates. Okay, so then of course we haven't really decided if this is a reaction yet, so we better check our rules. And our rules say for sulfides, start with sulfide. Sulfides are insoluble, but lithium is an exception. So lithium sulfide would be soluble, which means aqueous, so no reaction yet. Okay. And then our rule for nitrates, if I recall, says that they're always soluble, right? So there are no exceptions to that rule. And so we are going to say aqueous here as well, which is another way of saying that this is a no reaction. So we don't need to balance it. And in fact, I'm just going to draw a big old line through those products because they wouldn't actually give us anything new. Okay, so that is a no reaction. The reason that this is a no reaction is because I've got these 4 aqueous ions floating around in solution, and then when they put them together in the same container, they're still just aqueous, right? So nothing has really changed. In other words, if we were to write the net ionic equation for this, everything would cancel because everything would just stay the same. All right, so I'm going to ask you to go ahead and take this reaction up here that we did a minute ago, this one that did work, and see if you can come up with the net ionic equation for it, and see what you come up with. Okay, so this is not quite the net ionic equation, but this is the complete ionic equation. And if we cancel spectator ions at this point, it looks like I have 2 sodiums on the left that are aqueous, and those same 2 on the right that are aqueous, and I also have 2 aqueous hydroxides and 2 aqueous hydroxides. And so what that leaves me with is an aqueous carbonate, an aqueous calcium ion coming together to form a solid calcium carbonate. So notice the reason I didn't split up the CaCO3 is because it was a solid. So when I wrote the ionic equation, that stayed together. So the only reason this is a reaction is because of that change. We went from aqueous calcium and carbonate ions separate on the left side of the equation to coming together to form a solid precipitate on the right side. So that's what makes this a reaction. If they had all just remained aqueous ions, like if I had gotten Ca2 plus aqueous and CO3 2 minus aqueous, they would have all canceled and that would have been a no reaction. So hopefully that makes sense and we will get more practice with this in class and in the lab.